Hi everyone, so my name's Dr. Matt Brough. I'm Director of the Rail Asset Management Group at Aecom. My original PhD is to do with sewage and soil mixing augers, so I have no idea how that is relevant to a room full of railway engineers. I have been studying trackbed engineering for about 20 years, so today I'm going to be talking about asphalt track developments and running through in 20 minutes the work we've been doing over about 2 years in developing asphalt track solutions for UK market. So first of all, if we talk about some failure mechanisms, in terms of formation failure, there's three factors which cause formation failure. Repeated dynamic loading from trains, fine-grained soils, cohesive soils, and excessive moisture content. And if we get those three factors together, we get these main sort of failure mechanisms. So we have progressive shear failure, sometimes known as trackside heave. We have excessive plastic deformation, where we get these characteristic localized failures and a ponding of water. And finally, attrition with mud pumping, effectively where we get the slurry fines pumping up into the ballast layer. And if we have those sort of failure mechanisms, it's obviously going to cause differential track geometry, repeated track maintenance, and in really bad cases, potential safety issues. In terms of the way we normally remediate that in the UK, it's quite a traditional solution. It's a ballast layer sitting on top of a sand blanket with some kind of geotextile. And the reported performance is about 25 years design life. But I think we all know that the performance of track is very limited by installation quality and ultimately how it's maintained. It's very dependent on drainage performance and ultimately the overall formation condition. And we do have some challenges at the moment with climate and weather, and as those change the way our assets behave, particularly around trackbed and earthworks, does this give the case for an improved life cycle resilient track form? And there is existing track forms on the market. There's a lot of slab systems out there. But typically, they're for very specialist problem sites, and the CapEx makes them typically prohibitively expensive. But there are other solutions available, and I've called Ballasted asphalt track a new track form. There have been studies before, but it's been very, very limited. What we're effectively talking about is just a ballast layer that sits on top of an asphalt layer, and beneath the asphalt layer, we can sometimes have sub-ballast or not have sub-ballast. And what are the benefits? Well, it effectively mitigates those three factors that I was talking about earlier. It gives us an increased modulus bearing capacity and improved load distribution. So we get less failure with the subgrade. Very, very importantly, it's an engineered layer. So that means we get a much greater uniformity of stiffness laterally and longitudinally along the track. And that has a big impact upon ongoing track quality deterioration. We get a nice impermeable uniform drainage layer. It's got benefits there. Reduced effects to freeze thaw. We can start to reduce construction thickness, which I'll talk about in more detail in a second. And overseas studies seem to suggest that you have reductions in the tamping cycles. There are costs. There's an increased CapEx cost associated with this type of track form. Not as much as slab, but it is still higher. For UK market, there are potential installation issues in the normal renewal constraints that we have to address. And there isn't much known about the asphalt layer in terms of how it actually deteriorates and fails. What do we do in terms of maintaining that layer, and what do we do at the end of its life? So some challenges. So this is an innovation conference, and I guess a question is asphalt track innovation? And if you look around the rest of the world, asphalt track has been used in many, many, many other countries for quite a long time. If you look to the States, it's used typically on heavy axle railways, often at maintenance liability sites. We look to Japan, they have 3 performance ranks of track. Their performance rank 2 track is an asphalt track bed. It's been installed for over 30 years. In Italy, on the Rome to Florence line, they have a 140-kilometre section of asphalt track, or ballasted asphalt track. On the French TGV line, they have several instrumented asphalt test tracks They're considering using it for more for their sort of high-speed network. Similarly in Spain, on their high-speed network, they've been looking at asphalt track. They've got various instrumented test tracks. And finally in Austria, throughout their traditional railway network, asphalt track has been used for quite a long time. And there are sort of reported installations as far back as 1963, where they've actually gone back, excavated the ballast out, and the asphalt layer is still performing. So there's lots of evidence of use. It's used for high-speed, traditional passenger railways. There's definitely long-term performance experience. In terms of the layers, in all these sort of instances, it's typically the same sort of layers. It's a ballast layer sitting on top of an asphalt layer, sitting on some kind of sub-ballast. The big change seems to be around the sub-ballast layer, which I think is more dependent on the type of railway that's been applied to, whether it's a high-speed or a freight railway. So if we're bringing a new track to the UK market, we've got an opportunity to innovate with this whole track form. And there's various areas we can start to look at. We can start to look at the granular layer. So what type of material will that granular be made of? What depth? Can that material be stabilised? The asphalt layer, for any pavement engineers in the room, there is a whole science behind asphalt mix design in terms of the aggregate type, the binder type, and the ratio of those materials. Do we want a hot mix, a warm mix, a cold mix, a foam mix asphalt, which has big sort of implications in terms of construction process? The sub-ballast, what sort of material, the depth of material, and once again, can we stabilise that layer? But if we are going to start messing around or changing those layers in some way, we need to work out how does it behave as a system in terms of what's the stiffness that all of those layers create as experienced at the railhead. We need to think about interfaces with the infrastructure and practical construction issues. So the RSSB launched a competition, the Avoidance of Bridge Reconstruction, which gave us the opportunity to explore some of these ideas and to challenge some of the current standards. And effectively the project was looking for ideas to minimise bridge recon required in electrification projects. And this obviously comes from the need to excavate through existing structures to accommodate gauge. So our idea was to develop thin track forms compared with traditional ballasted solutions and reduce the actual excavation depth. And what we're actually talking about in terms of depth is a typical ballast depth of about 350 and blanketing sand of about 100 millimetres. That's the benchmark that we're trying to sort of reduce the depth from. So we started a three-phase project with the RSSB. Network Rail was an external stakeholder guiding the project. And we went through 3 stages: optioneering, proof of concept, element scale testing, looking very much at the materials, and then long-term system testing and development. And I'm just going to talk you through high level some of the findings of the study. So in terms of phase 1, we first of all needed to understand the benchmark solution in terms of the depth, the materials and the functions that they provided. And the current requirement is for 450 millimetres below sleeper bottom to accommodate the standard. What we then did was we worked with our pavement colleagues and we looked to the construction industry to see if there were other products that we could bring into rail and that could potentially be applied in track in this new track form. We then packaged up those different solutions into 13 composite solutions that we assessed and deemed still addressed the functional requirements of the benchmark solution. We then did some quite simple linear elastic modelling, and purely the aim here was to try and reduce the material thicknesses so we could achieve comparable levels of settlement, sleeper end stiffness and shear stress when we compared to the original benchmark. Once we'd done through that process, we then agreed criteria with Network Rail, contractors, the train operating companies that were important in terms of any new track form. We went through a value management process and we ended up with 2 preferred solutions that we wanted to study in more detail. So the 2 solutions we ended up looking at or taking forwards to further studies was a ballasted asphalt track solution and a GeoWeb ballasted track, and there's a presentation later on GeoWeb track. We installed these both in our test facility. We effectively simulated a poor subgrade, good subgrade, and we built these railways using traditional renewal techniques. The effective aim of that was to prove the concept, to try and test the installation, and to compare the trackbed stiffness with benchmark solution data. And at the end of this particular phase of the project, we ended up with some track forms which were 11 to 22% reduction in below sleeper bottom construction depth, a track form that was maintainable using traditional techniques such as tamping, and we'd also validated the stiffness, that it was equivalent to the original benchmark. But we wanted to try and push the aggregate and the asphalt design further, because our aim was to try and reduce depth. Typically, the aggregate depth of material choice is limited by the current specs, so in terms of load transfer, drainage, maintenance requirements, and the maximum particle size to depth ratio. But for the particular scenario with avoidance of bridge reconstruction, we're looking at quite short length of track. So we can maybe assume an alternative maintenance regime, so for example, measured shovel packing. And also considering the material is going to sit on top of an asphalt subbase, it allowed us to rethink the aggregate layer as to what it actually could comprise. So we looked at a whole range of different materials that we could use as alternatives to ballast. That ranged from alternative materials to modified size, smaller aggregate materials to stabilised materials. And once again, we did a value management exercise where we looked at the functional requirements of those materials, how they would be applied in track, to come up with some ones which we wanted to study in more detail. And at the end of that process, the main benefits seem to be associated with the modified sized or reduced sized aggregates and bitumen stabilised aggregates. We obviously needed to try and validate that material in some way. So we've got a bespoke rig at Nottingham for testing aggregates or stabilised materials. And effectively, the machine allows the sides to flex, so it's more realistic of how those materials will behave in a railroad environment. We carried out quite a large testing regime of the modified size aggregates and the bitumen stabilised aggregates. And typically the outcomes from that work, they identified these modified size aggregates as a real contender for potential use in this new track form. Relatively good performance in the rig compared with the ballast. The bitumen stabilised aggregates, we had bitumen emulsions to the aggregates. They also showed promising results. They got better resistance to permanent deformation and particle deterioration. And the positive effect was even more pronounced in these reduced size aggregates. Practically though, although stabilisation with bitumen emulsion does look a positive thing, before we take that forward, we really need to think about the maintenance methodology. How would we maintain a track that has been stabilised with bitumen? But what about the asphalt? I'm not a pavement designer, as I said at the start, but asphalt can be designed to address a whole range of conflicting requirements. So deformation, cracking, durability, water resistance, traction. It needs to be inexpensive, readily made and easily placed. And if we look at the whole science behind asphalt, we can look at the aggregates, we can look at the binder, we can look at the aggregate binder ratios, ultimately to try and get the performance requirements that we're trying to get out of that particular layer. Now, if we've got an asphalt layer and a track bed, it's less onerous than you would normally have on a traditional highway. The failure mechanisms are going to be different, and they're obviously going to have less impact. So our pavement research team have looked at various options that we could use for the asphalt mix design in this particular solution, which is something that we've taken on for further study. So at this point in time, we've got a thin depth asphalt track bed. It comprises reduced size aggregate that sits on top of an asphalt layer, then sits on top of a sub-ballast. And there's a whole range of different depth combinations that we could have with that. If we look at the modified size aggregate layer, we're looking at 100 to 200 millimetres, the asphalt 75 to 100, and the sub-ballast 50 millimetres. We modelled, again, lots of those combinations to see how they would perform. Typically, they gave equivalent performance to standard ballasted track, but very importantly, with this reduced depth, which is one of the key aims of the study. And the next stage was to validate longer-term settlement performance of these solutions. This work is still in progress. We're still analysing the results. This was work that we've done with Southampton University. We've made 6 full-scale samples of the proposed asphalt track construction, tested over 3 million cycles at 3 hertz. And the aim was to try and understand the impact of varying the depths of this asphalt layer and the aggregate layer. As I say, results still being analysed, but the initial analysis suggests that we've got equivalence between some of the solutions we're proposing and standard ballasted track. We do think there's a limiting factor. We think about 250 millimetres depth for the combined asphalt, sub-ballast and aggregate layer. And there's a definite minimum depth for the asphalt. We think of about 75 millimetres. We're currently looking at life cycle cost analysis of the different track forms. We're currently challenging our assumptions with Network Rail, but at the moment it's looking positive. As I said earlier, you've got an initial capex, which is higher, but the net present value seems improved for asphalt track. So this is maybe a word of warning or advice more than anything else for innovators in the room. We're currently writing our final report for the Avoidance of Bridge Reconstruction. We're quite pleased with the outcomes and areas for which we can take forward for further study. But we decided to go through like a formal assessment process with Network Rail to assess the rail industry readiness level. And if people don't really understand what that is, then you should get your head around it. But it's goes through various readiness levels: technology readiness, manufacturing readiness, integration readiness, etc. And your rail industry readiness level is only as high as your lowest level. So through our research, we have definitely pushed forward on several of the readiness levels. But our system readiness was viewed as only being one. So effectively, we've agreed some things that we can do to increase that rail industry readiness level. But I guess the point I'm making is that if you want to innovate and bring something to market, you need to be assessing all of those different aspects. One thing that did come out of going through this process was that the wider asphalt track benefits are recognised outside of the Avoidance of Bridge Reconstruction remit. They're both very different products with benefits. But with what you would class as standard asphalt track, there are probably less challenges to implement in the UK rail network. So in terms of conclusions, the R&D has demonstrated the feasibility of a shallow depth track form using ballasted asphalt trackbed. We need more work to do to progress the rail industry readiness level, which was something we're doing at the moment with our client and Network Rail. The current work has challenged some of the existing trackbed material and design principles, which I think raises some interesting questions or further studies for industry. And I guess just final point, asphalt track is not new. There are many examples of in-service use with long-term performance data. Presents an interesting opportunity for the UK rail market, and I see it as a more resilient track form that mitigates traditional formation issues with potential improved life cycle costs. Thanks for listening.